In today's Embedded Systems Minute, let's talk about latches. We use latches to store values in digital logic. The latch allows us to keep that value locally rather than having to go off to memory to get the value. The SR latch was commonly used in technologies like TTL. It uses cross-coupled gates. But TTL isn't often used today because it consumes more power. We rely on CMOS technology, which operates on fundamentally different principles. And as a result, we want to design latches differently for CMOS than we did for TTL. Let's understand the difference by starting with the SR latch and then moving on to the CMOS latch. This is the schematic symbol for an SR latch. The S stands for set, and the R stands for reset. Q is the data output, the value stored in the latch, and Q prime or Q bar is the logical complement of that value. We build the SR latch out of cross-coupled logic gates, in this case NOR gates, but we can also use NAND gates. If we want to store a 1 in the latch, we first set S, the set input, to 1. And then the Q output becomes 1, and the Q prime output becomes 0. Now if we remove that value from S, so S is now set to 0, the latch retains that 1 value. The arrows here show the flow of current between the two cross-coupled logic gates. That current is what stores the value in the latch. If we want to store a 0 in the latch, we would temporarily set the reset or R input to 1. That would cause Q to be 0 and Q prime to be 1. The SR latch we just saw was common in TTL technology, but CMOS operates on different principles. Whereas TTL relied on currents flowing to maintain values, in CMOS we can use charge. That allows us to build latches in a fundamentally different way. Let's take a look at the CMOS latch. This is the schematic symbol for a D latch. D is the data input where we give the value that we want to store. Q is the output of the stored value of the latch. In this case, we'll see that our latch will naturally produce the complement of the stored value, so we call this Q prime or Q bar. The triangle on the bottom represents the clock input that we use to control when the latch reads that D input and stores the value in the latch. This is a transistor schematic for the D latch. On the left side, we have an inverter. On the left side, the two transistors form a transmission gate, or a form of switch that is either on or off. So the clock input in its true and complement forms controls the transmission gate. The inverter provides a parasitic capacitance. That capacitance is part of the transistor structure. It's not a separate component, but we can take advantage of it to store logic values. We'll use the transmission gate to control access to that parasitic capacitance. When the clock is enabled, the transmission gate is on, and the D input is connected to that parasitic capacitance at the inverter. So we can either charge that parasitic capacitance to store logic 1, or we can discharge the capacitance to store a logic 0. When we disable the clock, the transmission gate is now off, and the D input is disconnected from the parasitic capacitance at the inverter. So the Q prime output is controlled by that parasitic capacitance through the inverter. And now you see why the natural output is Q prime and not Q. So the transmission gate allows us to control when we load the latch. If we didn't have the transmission gate, the Q prime output would simply follow D whenever. We couldn't have it store a value so that we can do something else with the D input. CMOS was revolutionary because it uses much less power than did legacy technologies like TTL. CMOS operates on different principles in order to achieve this improvement. It uses charge to represent values. That means that we don't have to rely on currents flowing continuously in order to maintain the value of a latch. So in CMOS, we use charge on a parasitic capacitance to store the value. That's very different from the cross-coupled gates that we need to use in older technologies like CMOS.